Okay, so now what about the other theory that learns not only what the probabilities are of the building blocks, but in fact what the building blocks themselves actually are for WH dependencies at the same time as it's learning their probabilities, right? What about that one? How does that work? So this is the theory that we're lovingly referring to as what the pieces are and their probabilities. Okay, so if you recall, the building blocks we looked at before, which came from Pearl and Sprouse's proposal in 2013, were pre-specified. The model child already knew to look for syntactic trigrams, units of 3, of a certain kind, right? Look for these sorts of pieces making up those building blocks, IP, VP, and that kind of thing. So just to be clear, look for groups of 3 units, and this is something I didn't necessarily point out when we were going through it before, but if the unit is a complementizer phrase, a CP, include the lexical item, subcategorize it. It's not just CP, it's CP that, or CP null, or whatever the complementizer actually is. So the empirical motivation for including the lexical item in the complementizer phrase was this. 2 of the islands, the weather island and the adjunct island that we looked at before, only differ from more acceptable WH dependencies like this one by the complementizer used. So in fact, this is an example from an embedded dependency with a non-island structure. What does the teacher think that Lily forgot? And to turn it into a weather or an adjunct island, you're really just switching the complementizer, well, as well as the verb, but the complementizer is one of the main things that gets swapped lexically. What does the teacher wonder? Whether Lily forgot. What does the teacher worry if Lily forgot? And you can really see this when you characterize the syntactic path, right? It's CP that versus CP whether versus CP if. Other than that, they look pretty much the same. So that's why the building blocks included that lexical item type. So here's the question. Is it the only lexical item that you need to include? And the answer is maybe not, right? So some data more recently from Liu et al. 2019 found that the acceptability of certain WH dependencies can depend on the lexical item in the main verb. So they have this kind of structure. What did she? Verb that he saw, so an embedded dependency complementizer, that main verb. What did she think? What did she say that he saw? These are pretty good. Versus what did she whine? What did she mumble that he saw? These are less good, right? And the only thing that seems to really be differing is the lexical item in the main verb. And in fact, again, if you characterize the syntactic paths, you can see this, like the thing that's differing is that verb in the main clause. So it seems like we need to include the main clause verb, at least sometimes. So the bigger question is, are there other lexical item types that the building blocks need to include, right? So let's sort of back off to our theory. What the child's trying to do is learn what the best, quote unquote, building blocks are at the same time as she learns about their distributions in the input, their probabilities. So before, we were looking for building blocks made up of groups of 3 units, and if the unit was a complementizer phrase, a CP, include the lexical item like these. These were the building blocks before. What if we're looking for the quote unquote best building blocks? Well, maybe the best size is sometimes bigger than 3, but sometimes smaller than 3, or sometimes actually is 3. So, for example, if we have groups of 3 units, again, maybe the best size says sometimes smaller and sometimes larger. So look for the best sized units, whatever those might be. And before, it was based on whether the unit was a complementizer phrase, we would include the lexical item, but maybe the lexical item is needed sometimes for some types of phrase nodes, but sometimes not, or maybe even sometimes it's needed, like here, verb phrase characterized, subcategorized by think, so including the lexical item there, but maybe not other times, right? Sometimes needed, sometimes not. And so it's sort of like sometimes include the lexical item, depending on what's best. So, okay, how can the child learn what the best building blocks are? Like, what does best mean, really, here? So here's the theory, is to look for a quote-unquote efficient set of building blocks, okay? And in particular, efficient building blocks here we're going to define as ones that allow the representation of current and future WH dependencies to be more probable. So high probability things are more efficient, Why? Well, one idea is that higher probability WH dependencies, higher probability things in general, are faster to process whether you're comprehending them or producing them. So that's why higher probability is more efficient in this sense. So you're looking for ones that allow higher probabilities for the things that you have seen currently and hopefully will see in the future. So how do you find such things? Well, we're going to propose that you look for building blocks that are a balance between how big the building blocks are and how fast they are to put together to make a WH dependency. So let me show you what I mean by that. So let's look at this one. What did she say that he saw? So this is an embedded clause with their complementizer that. You can sort of see a version of a structure here that has all these different pieces. We can simplify that using our syntactic path notation, where we're really just focusing on the path between where that WH word is understood and where the WH word was actually spoken. It looks something like this. Okay, this is what you're trying to make high probability. So what can you do? Well, you can have a bunch of small pieces. You can, in fact, have each individual little piece be something that you use, so that many of these small little pieces make up a WH dependency. But it may be slower to put together many small pieces because you have to put them all together. On the other hand, it may be faster to put them together if they're often reused, so they're easier to access, right? You reuse them often. Here, even within this dependency, we're reusing these pieces, and across dependencies, we're using these same pieces, right? So if they get reused a lot, they may be faster to access. Now, the other sort of extreme is that pieces can be big. They can be so big that you just say have one piece per WH dependency, right? And in that case, it's going to be faster to put together one big piece because you're not putting anything together. You're just boop, it's done, right? But it may be slower if the piece is used rarely because you have to access that piece in the first place. And you're probably not reusing it that often most of the time. Each dependency is getting its own piece, so maybe slower, right, to use that piece. So you have these two sort of endpoints, many smaller, one big, and so the most efficient option is probably a balance of bigger and smaller blocks that collectively are faster to put together for whatever WH dependency you might encounter on average. And so maybe here's one example. You have some bigger pieces, some smaller pieces, right? One of many possibilities. So how can children find the best balance, right? Like that's the question. And so what we're going to do is use the approach that was used by O'Donnell in 2015, is to use Bayesian inference to search through the hypothesis space of all possible building blocks and find an efficient set for children's input, right, that makes it high probability. So that's what the model child is going to do, right? It's going to try to find those pieces that make the current input high probability. So keeping that in mind then, what target behavior are we trying to capture? Well, we've had the WH dependencies from before, but there's additional target behavior about WH dependencies that we'd like to capture. So before, again, we were looking at certain adult judgments, certain child preferences for WH dependencies. But, right, in fact, as a reminder, some judgments about subject islands, complex MP, weather, and adjunct island stimuli, looking for a certain type of pattern of judgments, looking for a certain preference in child target and child behavior between one WH dependency and another. And now we're going to have that plus additional target behavior, right? So we're looking for the behavior where we look at the varying main verb frequency, right, from Liu et al. 2019, where we want to see a difference in acceptability based on that main verb. In fact, the particular pattern is pretty simple. If you have the frequency of the main verb on the x-axis and how acceptable it is on the y-axis, what you see is a positive correlation. You actually see different types of verbs, which for the purposes of this paper mattered. For our purposes, we don't have to pay attention to that too much. The important thing is simply the positive correlation between frequency and acceptability. The more frequent, the more acceptable, right? So that's the pattern, the positive correlation between main verb frequency and judged acceptability. Now, On the child's side, before we had an interpretation preference, right, given a potentially ambiguous WH dependency. But in fact, from that same paper, de Villiers et al. 2008, there are other WH dependencies that they investigated, actually. Who did the little sister ask how to see? Who did the boy ask what to bring? How did the mom learn what to bake? How did the girl ask where to ride? How did the boy who sneezed drink the milk? And this is, one way to sort of think about the relevant island crossing structure, the types of islands, versus the comparison interpretations. And in every case, these children seem to prefer, right, the comparison interpretation that doesn't involve crossing these island structures. Okay, so that's the behavior that we're looking at from the children, or the model children in this case, right? That's our target. You want to have these adult patterns, these child patterns. So what does the model child do, right? The model child is trying to learn the best pieces and their probabilities from the WH dependency distribution that we have in order to generate that target behavior. And here's what we find. So for the target behavior, first of all, for the first set of adult patterns, we do see super additivity predicted for judgments of all 4 island types, right? We get that pattern where you really don't like the dependency that crosses that island structure. You dislike it more than you perhaps should, as it were. And now what about the positive correlation? Well, we get that too. There is a positive correlation predicted with verb frequency for judgments of this particular WH dependency, where the main verb is the thing that's varying, and this is the judged, this is the probability which can be mapped to the judged acceptability. So we get that too. And in fact, when we look at children's preferred interpretations, they do prefer the model child, children prefer this one. And the model child in this case finds this one to be 10 to the 5th times more probable, so like 100,000 times more probable is pretty good than the other one. That's the right preference. Fantastic. Our model child is preferring the one that children prefer, and also prefers the child preferred ones for the other WH dependencies I briefly mentioned, right? So we're getting the right patterns both for adult behavior and child behavior. So fantastic. Great. Now, here's the interesting question. What do the building blocks look like that this model child learned that actually lead to this observed behavior? Like, what are they? Right? What are the best building blocks? Well, it turns out, in fact, they are different sizes. Some are very small, some are very large, right? And there is some lexicalization. It's based on frequency. So more frequent lexical items are attached, are used, right, in the building blocks, right? So for example, you might have verb go and verb say as their own pieces that might get separately attached to a verb phrase with a verb in order to make a verb phrase that involves go. But if you have the verb know, well, that's all one chunk, because apparently it's used often enough that it's much more efficient just to chunk it. And you can see this showing up in other types of building block instantiations. The interesting thing, I think, is that the frequency threshold is learned by the model child. There's no set threshold. It figures it out on the basis of the input. And you have a different one for each node type, right? The threshold for verb phrases is going to be different from the threshold for complementizer phrases, which is going to be different from the threshold for inflectional phrases, and so on. And, again, sometimes sometimes the lexical item is included, and sometimes it isn't, right, within that node type. So it's not like you always lexicalize the verb. It's like, no, you lexicalize the most frequent ones, and the other ones you leave separate, right? Okay. So that's cool, right? We have a sense of what the representation is that's actually being learned that could generate the observed behaviors that we're seeing. And the larger takeaway is that this theory, where we're learning not only what the probabilities of pieces are, but what the pieces themselves are, this theory can work even better for learning knowledge about syntactic islands. And the key idea, again, like before, is that learning about the building blocks, those pieces that are composed locally in order to create WH dependencies, learning those building blocks leads to knowledge about syntactic islands without trying, right? Even when there's also less knowledge built in about what the building blocks themselves look like. So what's the key idea here? This strategy works when the child's goal is finding efficient building blocks, ones that make the input high probability.